Weird. Okay, I apologize for that. Live streams are always fun. There's always something weird that goes on, and there it is. The weird thing, I tested the audio just before I went live, and everything was going fine. So I was just waiting, sitting there waiting for the countdown timer to go down, running through my slides, and for whatever reason, my mic driver decided to die on me. But we're back. We're live. Sorry for the technical difficulty. Thanks for bearing with me, and welcome to the stream. Okay, cool. Great. So the plan for today is to talk about routers. So hopefully most of you have seen the Networking Fundamentals video series. That's a video series that I've been putting together over the last 3 or 4 months. And the plan is for that series to teach anybody about networking. So whether you're a junior network engineer just getting into the field, or whether you're a sysadmin or a system engineer or a programmer or a manager of such techs, and you're just looking to get a better idea of what the networking guys do all day. I should say the networking folks do all day during their day-to-day operations. So that's the plan for the Networking Fundamentals series. So far in the series, I am 4 lessons in, and each of them have been 2 parts, so 8 videos. This lesson, the one we're going to go today, is going to be part 1 and part 2 of lesson 5, which is going to discuss routers. Doing this live as a test stream sort of lets me demo the material and make sure that everything is fluid and everything is consistent, so that when I go to record the final published, polished version, everything is nice and smooth, and it makes watching the videos hopefully as easy and as simple as and require as low cognitive load as possible. The idea is you only need to watch them once to get an idea of what's going on, and it's not something you're going to have to throw hours and hours and hours at. At least that's the plan. So today we're going to run through the routers lesson, and there'll be an obvious part where we'll take a break between part 1 and part 2, and I'll go to answer questions to the chat. To start, go ahead and tell me. So I just saw from Peru, Juan, welcome to the chat. If you're, rather, tell me in the chat, where are you from? It'd be cool to see just where everybody else is joining us from. Personally, I'm in Hawaii at the moment. I normally live in Seattle, but I moved to Hawaii about 8 months ago or so. Yeah, in December. Cool. We've got the UK, we've got Canada, fantastic. The Philippines, awesome. Welcome. Connecticut, welcome. Whoa, the Philippines. What time is it for you over there, Carl? Ohio, cool, awesome. Poland, also welcome. Oh, 8:40. Okay, not as bad as I would have expected. Awesome. Well, great. Well, I'm glad you guys are here. Glad you guys are gonna join, and without further ado, and hopefully without any further technical difficulties, let's get right to it. Cool. So you are all here to see the routers video or slides, and let's get into it. So as I mentioned before, this is the lesson on routers. It's a 2-part lesson, and we're going to do both parts today on the live stream. And this is again the next lesson in the Networking Fundamentals video series. So let's get right into it. So if you haven't watched the rest of the videos in the Networking Fundamentals series, I would highly recommend starting there. In lesson 1 of that video series, we went through the discussion on what networks are. We discussed that networks are a logical grouping of hosts. So over here, all 3 of these hosts are all in a logical group. They're of similar type, similar purpose, similar intent, and same thing over here. And we also discussed the purpose of switches, which is to facilitate communication within a network, meaning this switch will facilitate the communication for those 3 hosts, and this switch will facilitate the communication for those 3 hosts. Then we discussed routing, which is the process of moving data between networks, meaning if these hosts want to speak to these hosts, they're going to have to run through a router, which is going to perform routing, which is what's going to take the data from this network and move it over to the next network. Now, it's important to understand the definition of routing as I've laid it out, because there are many types of devices that do routing. So there's load balancers, there's proxies, there's forward and reverse proxies, there's firewalls, there's layer 3 switches. All of those devices claim to do routing. Well, what we are going to discuss today are the rules of routing. So what we discuss together, what a router does, is actually the same thing that any of those devices also do. They're just the rules of routing. The benefit then is understanding what we discussed today will teach you not only how, say, Cisco routers work, but also how Juniper routers work, or Arista routers work, or any other router in general. You could configure your laptop to become a router, and your laptop will be following the same rules of routing that we're going to discuss today. In any case, that's all the stuff we covered in Lesson 1. In Lesson 2, we discussed the OSI model, which is the framework for understanding how data moves through a network. Specifically, the important part to understand with Lesson 2 was the interaction between Layer 2 and Layer 3. We taught that by showing you an example of this host sending some data to this host. The way it did so is by adding a Layer 3 header to that data, which included a source IP of the sending host and a destination IP of the receiving host. Then, the host had to add a new Layer 2 header. I should say a new Layer 2 header was added and removed at every single hop on the path to account for jumping between router to router all the way until it got to the final host. That is the interaction between Layer 2 and Layer 3, and we discussed that in Lesson 2 of the Network Fundamentals series. Then, finally, in Lesson 3, we started to discuss everything that the hosts do insofar as network communication. We showed you an example of host A trying to speak to host B when they were directly attached to each other. Well, after we went through the steps, I let you know that the steps that host A followed to talk to host B when they are directly attached are also the same steps that host A would follow if there was a switch in the middle or multiple switches in the middle. The hosts themselves don't actually know whether there's one switch or two switch or any number of switches between who they're speaking to. So they're still going to follow the exact same steps. The thing that's different is what a host would do if it's speaking to something on a foreign network, and that was what we discussed in Part 2 of Lesson 3. We showed you everything that host A would do in order to get a packet to host C, which is behind a router on a foreign network. And again, everything that host A would do would be the exact same if host A was connected, if there's only one router between host A or host C, or if there was 3 routers between host A and host C. One way or another, the hosts are going to follow the same rules that we discussed that hosts do when they're talking to other hosts on the same network and other hosts in a foreign network. Both of these discussions allowed us to discuss the fundamental role of ARP, or the Address Resolution Protocol. Now, ARP is a crucial protocol in understanding how data flows through a network. It's what links Layer 2 and Layer 3. We discussed ARP and showed you how ARP works in Lesson 3, but you'll see in Part 2 of this lesson, there's also going to be an implication of ARP, so it's important to understand everything you see on your screen now before we get into our routers lesson. And again, if any of this doesn't make sense, feel free to go and watch those videos. You can pause this live stream and come back to it later if you need. Finally, we get to our lesson. Now, not pictured here is Lesson 4. In Lesson 4, we discussed switches. Feel free to review that. We are not going to be talking about switches in this lesson because we've already talked about them. The purpose of this lesson is to discuss routers. I'm going to show you everything that occurs to get data through a router, either to an end host or to other routers as necessary. Cool. So here we go. So here we have a network. This is the 10.044.x/24 network. On this network are 2 hosts, host D and host A. Now for these networks to actually be attached to this network, for these hosts to actually be attached to this network, first they need to be connected to the switch that's facilitating all the communication within the network. That attachment is going to happen on the switch's NIC, on the host's NIC, or network interface card. That NIC has a MAC address, which is the physical identification of that particular NIC. Now we discussed this in lesson 2 when we discussed the OSI model. We talked about Layer 2 addresses and MAC addresses. That's where these numbers are coming from. So this is showing you the NIC, the MAC address of host D, and the MAC address of host A. Now, normally a MAC address is 12 hex digits. I'm only showing you 4 to make it smaller on the slides. Either way, for these hosts to speak, they must be connected to a switch, and they must have a MAC address, and they must also have a Layer 3 address, like an IP address. Host D's IP address is 10.044.3, and host A's IP address is 10.044.9. That's what it takes for these hosts to speak to each other. Now, routers also are connected to networks. And just like those hosts had an IP address and a MAC address, the router is also going to have an IP address and a MAC address. In fact, the IP and MAC address work the same way for the router as they do for the hosts. It's the same thing. This is the layer 3 identity of the router, and this is the layer 2 identity of the router. And each of those addresses will be used in hop-to-hop or end-to-end delivery as necessary. Now, again, we discussed switches in lesson 4 of this series. For this lesson, I want to reduce all the variables possible, so we're going to remove switches entirely. Just assume that they're still there and anything in this box is attached to that switch. But for what we want to focus on, just routers, we're going to avoid looking at switches for now. Of course. Okay. So, if routers need an IP address and a MAC address, just like hosts, right? We have to then ask, what exactly is the difference between a router and a MAC address? Well, there's a few different ways, between a router and a host. Well, there's a few different ways to answer that question. And my favorite definition for router and host actually comes from the IPv6 RFC. Now, if you're unfamiliar with RFCs, they stand for Request for Comments. It's essentially the way that internet standards are written. So if you're ever having a nerd argument with someone discussing how a particular protocol works, whoever can quote the RFC generally wins the argument because the RFC is essentially the Bible for network engineers. Either way, in the IPv6 RFC, you have these 3 definitions. So you have a node, which is any device that implements IPv6, but that definition also applies to IPv4. So a node, you could say, is anything with an IP address. A router, then, is any node that forwards packets also not explicitly destined to itself. That's the major difference between a host and a router. Notice a host is simply any node, so anything with an IP address that doesn't forward packets not explicitly addressed to itself. Meaning, if this packet were to show up on host D would look at the destination IP address and see 8888 and be like, oh, that's not me, I'm just going to drop this packet. But if this router were to receive this packet, this router would look at the destination IP address and be like, oh, that's not me, but let me see if I can figure out how to get this to 88888. That is the difference between hosts and routers, is that routers are going to try to forward packets not destined to themselves. Now, in order to forward packets not destined to themselves, we have to have other destinations that exist. For now, our topology only has one network. So let's go ahead and add another network to our topology. Just like over here, in order to attach the router to the 10044 network, we had to configure the router with an IP address and use the router's NIC, therefore its MAC address. This process is going to have to repeat for every interface of the router. So in order to connect router 1 to this network, we're going to have an IP address and a MAC address in this network as well. This is actually what connects the router to the network, is configuring an IP address in that network. Cool. Now, in order to do this forwarding packets not destined to themselves, routers need to maintain a map of all the networks that they know about. That map is known as the routing table, and it contains information information about every network that the router knows about. For this particular example, for R1, there's only going to be 2 entries in R1's routing table. One entry for the 10055 network and another entry for the 10044 network. The way it works is those entries are going to provide information to R1 about how to deliver packets. So that if R1 receives a packet with a destination IP address of 10044.9, router 1 will look into its routing table to see if it knows how to get to the 10044 network. It does. It knows it needs to go out the right interface. Now, normally, router interfaces would be something like FA01 or Gig01 or ETH1, ETH2, and so on. But for the sake of simplicity, in these slides, I'm just going to use the right interface and the left interface. Okay, so that's your basic rundown on routers. But this routing table is actually very important. It's actually a large part of what network engineering is about, is making sure that the routing table has the entries necessary so that the router can deliver packets as needed. So we have to speak in a bit more detail about the routing table. There are 3 ways for a router to learn entries in its routing table. Those The first of those three ways is what's known as a directly connected route. And that's actually the example we just gave you. A directly connected route appears in the routing table anytime a router is directly attached to a particular network. So for R1 connected to this network and this network, it's going to have two directly connected routes. One of them for the 10.5.5 network out the left interface, and the other one for the 10.0.4.4 network out the right interface. If this looks familiar to you, it's because it's the exact same thing that we had a moment ago over here, showing you R1 in simpler terms. Cool. So let's add another network and another router in between the 10.0.6.6 network and the 10.0.5.5 network. R2, just like R1, is going to have its own routing table. The routing table is not shared or mutual. Every router has its own routing table. And in each case, the routing table is going to have entries which tell this router or this router how to send packets. Well, just like R1 learned two directly connected routes by being connected to two networks, R2 is going to be the same way. As soon as we configure an IP address on R2 in the 10.0.5.5 network, it's going to learn about the 10.0.5.5 network out the right interface. And as soon as we configure an IP address on R2 on its left interface, it's going to know that the 10.0.6.6 network exists out the left interface. Now, both of these routers can use their routing table to deliver packets. If this packet shows up on R2, R2 is going to look at the destination IP address 10.0.5.5.8, look into its routing table to determine if it has a route for the 10.0.5.5 network, which it does. It's going to know that this packet needs to be delivered out the right interface, and it's going to send it along. But what happens if R2 receives this packet? This packet is destined to 10.0.4.4.9. That's host A's IP address. But if we look at R2's routing table, we don't have an entry for 10.0.4.4. At the moment, R2 doesn't know of the 10.0.4.4 network, which means R2's only option is to drop that packet. You see, when a router receives a packet that it doesn't know how to deliver, all it can do is drop that packet. The route table is essentially a map of every network the router thinks exists. So if this packet shows up and R2 doesn't have that network in the routing table, R2 will assume that that network doesn't exist and will simply drop that traffic. So it doesn't make sense to try and connect every router to every single network in order to avoid routers not knowing about these networks. But you'll see with directly connected, a router only knows about the networks they are directly connected to. So we need more methods for how to populate the routing table. And that's what the remaining two methods are going to be about. So the first method was directly connected. We just talked about it. Next method is static routes. A static route is a router being told by an administrator about the location of a particular network. For instance, I, as a network engineer, can log into router 2 and I can tell router 2, listen, if you want to get to the 10.0.4.4 network, go ahead and send it to this IP address right here, 10.0.5.5.1. Go ahead and send it to R1. Now, if R2 received that same packet, it'll look at the destination and be like, oh, this is trying to get to 10.0.4.4.something. I should send it to this IP address. And then router 1 will look at its routing table to determine that the 10.0.4.4 network is out the right interface and deliver it to host A. So that's what a static route is. But what happens if host A responds? Well, if host A responds, host A will be sending something to the destination IP address 10.0.6.6.7. But at the moment, router 1 doesn't know about the 10.0.6.6 network. I could tell router 1 how to get to that network by giving router 1 a static route. So you see this static route can work in either direction. But the key is that a static route is providing information about a particular network and how to get there, and who provided the information is the network administrator themselves. So it's a manual process. I had to tell R2 about the 10.0.4.4 network, and I had to tell R1 about the 10066 network. So that's what a static route is. The last way that a router can learn entries in the routing table is what's known as a dynamic route. A dynamic route and a static route are actually very similar. The only difference is who tells the router about the route. With static routing, the admin told the router about the route, and with dynamic routing, the routers told themselves about the routes. The way it works with dynamic routings is the routers themselves are going to talk to each other and tell each other about the networks that they know about. So let me get rid of those static routes and let me show you. So in this particular example, R1 knows about two directly connected routes, the 1044 and the 10055. It's going to talk to R2 and it's going to tell R2, hey listen, I know about the 10055 network and the 10044 network. R2 is going to be like, oh, well, I already know about the 10055 network, but I don't know about the 10044 network. I'm just going to send anything for the 10044 network to R1, to you, and then you can deal with it from there. That's what a dynamic route is. But it's also going to work in the other direction. R2 is going to do the same thing. It's going to be like, listen, I know about these three networks, and R1 will be like, well, I know about these two, but anything for the 10066, I'm just going to send it to you, to the 10552 network, IP address rather. So that's what a dynamic router is. Sorry, a dynamic route is. Now, I want to point something out about these two things. I'm going to back up a bit. Notice that the static route and the dynamic route included the same information. The only difference is who told the router about it. If the admin told the router about it, that's known as a static route. And if the routers told each other about it, that's known as a dynamic route. Now, how the routers communicate and share information about the networks they know about is governed by what's called a dynamic routing protocol. Here are some examples of 5 different dynamic routing protocols. Each of them differ in how often the routers communicate, what the routers share when they do communicate, how much control you have or of what is shared and what you share with your partner. All those are differences in how each of these operate. Now, the inner workings of each of these are actually pretty interesting and pretty fascinating, but they go well deeper than we mean to go in this series and in this course, or at the very least in this module. So for now, I simply want to introduce to you the concept of a dynamic route, and then tell you that each of these are simply different dynamic routing protocols which facilitate the communication between the two routers. Cool. So that is the first major part or breaking point of this particular lesson. It's understanding the importance of the routing table, understanding that every router has their own routing table, and understanding the 3 ways of populating the routing table, which gives the router information about the networks that it can send data for, or to. Now, in part 2 of this lesson, I'm going to show you every single step that is required for host A to send a packet to host C, meaning everything that happens to get the packet to R1, what R1 is going to do, how it's going to get the packet to the other side, how R1 is going to get it to R2, what R2 is going to do to get it to the other side, and then finally to back to host C. Then I'm going to show you the response traffic, and you're going to see the response traffic will go much quicker. But before we do that, there's one other idea that I want to leave you with before we close part 1 of this lesson. And it has to do with something we discussed back in lesson 1. Back in lesson 1, I showed you this topology. I used this topology to explain the idea of hierarchical IP addressing and that networks create the hierarchy using the routers that they're attached to. What I mean to communicate now to you is that routers are what create this hierarchy. So down here, we have routers attached linearly. But more appropriate to real life, you'll see routers connected in this hierarchy. The reason is that the hierarchy, we'll say topology, tends to scale better than a linear topology. So let me explain that. Let's say the Tokyo office of the Acme Corporation currently has 3 teams, but let's just say they add 2 new teams, the accounting team and the help desk team. Well, notice in each case, the new team gets its own router, and then that router plugs in to the aggregation router above it. But let's just say for a moment that these routers were not connected in a hierarchy, that instead they are connected linearly in a line. Well, what you'll start to see is that for the sales team to get to the internet, they can get there by only crossing 2 routers. But for every new team you add, they now have to cross every router you've already added before they can get to the internet, which means as you grow more teams, your network is going to get slower. That's not ideal. Whereas if everything was connected in a hierarchy, what happens is regardless who is trying to connect to the internet, if it's the sales team or the help desk, they're going to simply bounce off of 2 routers before they actually get there. So routers are typically deployed in a hierarchy to facilitate scale. Now there's one more reason that routers are deployed in a hierarchy, and that has to do with each of the router's routing tables. So let me explain that. Let's take a look at this router for a second. This router over here has to have one route to get to the sales network of New York, another route to get to the engineering network of New York, another route to get to the marketing network of New York, and then a 4th route to get to the sales team of Tokyo, 4th route to get to 104066, and then a 6th route to get to 104077. But notice these last 3 routes all start with 10.40 and all go the exact same direction. Well, one thing you can do to simplify routing tables is to do what's called route summarization. I can simply tell I can tell this router right here that to get to anything that starts with 10.40, just go this way. I don't have to actually tell this router about each individual network behind the 10.40. I can just say, go this way. That's going to improve the efficiency of the routing table and reduce the complexity. Moreover, this hierarchy also allows me to do what's known as the ultimate route summarization, and that's this route right here for the 0.0.0 network ID and the /0 mask. This network ID and mask include every IPv4 address, every address in the IPv4 internet. This is what's known as a default route. For instance, take a look at this router right here. For this router to get to the 1020.66 or 1020.55 network, it's going to have to go this way and then on, and then this way and then on. To get to anything in Tokyo, it's going to have to go this way and then on. And to get to anything on the internet, it's going to have to go this way and then to the internet. You'll notice that no matter what, everything that this router sends always goes this way. Well, why complicate things by telling this router about all the different networks that exist in the Acme Corporation and all the different networks that possibly exist on the internet? You can simply tell this router a default route, telling this router that, listen, to get to anything, go that way. That is another benefit you get from this hierarchical deployment of routers and networks and IP addresses. Cool. So that is the default route works very similar to a host's default gateway. It's simply telling the host how to get to anything else, go to a particular router. And that, my friends, wraps up the first part of our lesson on routers. The key points for this lesson are that routers have IP addresses and MAC addresses for each network they are connected to. Routers maintain a routing table, which maintains a map of all the networks that the routers know about. And those routing tables can be populated in 3 different ways. And finally, that routers are connected in a hierarchy to facilitate scale and route summarization. In the next part of this lesson, I'm going to show you everything that needs to happen to get a packet from host A to host C, and for host C to respond by sending a packet back to host A. But before we do that, now is a good time to take a quick break and turn it over to the chat, and let's just see if there's any questions that I have to catch up on. So I'll ask you guys, how did that go? What did you guys think of that lesson? Did you guys enjoy learning it in the way that did? What was good? What was bad? Feel free to throw that in the chat. Otherwise, let me go and look back through the chat to see what questions exist. So Ali asked about MME protocol route. I'm not really sure what that means. Go ahead and elaborate on that question if you can. Cool. Kalesh, I don't know if I'm saying your name right, but congratulations on mastering subnetting. I'm so glad that my videos were helpful in that. Hello, Tony from Philly. Welcome, welcome. Cool, no questions, Tony. Awesome. Gabby from Lagos. Excellent, welcome. Cool, Ali, glad you're enjoying it. And Venkatash asked about load balancing and routers. Yes, routers can do load balancing, but it is outside the scope of this particular content, we'll say. I did create actually another video that talks about what they call ECMP, or equal cost multipath. It's a way for routers to do load balancing. Feel free to look that up on my channel, or stick around. I'll get you a link afterwards. Cool, cool, awesome, John. Glad you enjoyed it. Fantastic. So with that out of the way, let's now continue and go into part 2 of this lesson. Cool. Okay, so in part 1, we talked through this topology. We talked through each of these routers having IP addresses and MAC addresses for each of the networks that they're connected to. And we talked through routers having routing tables and the different ways that routing tables can be populated. So here are the routing tables that we looked at in the last lesson for R1, and the routing table that we looked at in the last lesson for R2. Now, in that lesson, we didn't tell you that routers also have ARP tables. The routing table is going to tell the router how to get to a particular network, and then the ARP table is going to still have a mapping of the layer 3 to layer 2 addresses, just like hosts also have ARP tables. So both of these routers, router 1 and router 2, are also going to have ARP tables that they're going to maintain. Uh-oh, my face is in the way. Cool. There, I'm not in the way. Okay, so notice R1's ARP table has a layer 3 to layer 2 mapping for every node in a directly attached network to R1. So on the 10.0.4.4 network, the only other node is host A with the IP address 10.0.4.4.9. And then on the 10.0.5.5 network, there are 2 nodes, R2 and host B. And there's the mapping for host B and R2 right there. And it's the same way for R2's ARP table over here. It's going to have an ARP entry for every node in a directly attached network. For the 10.0.6.6 network, the only other node is host C. Is host C. And for the 10.0.5.5 network, R2 is, you could say, neighbors in a way with host B and R1. And there's the ARP entries right there. So just like a router has a routing table, routers are also going to maintain these ARP tables. But here's the difference. The ARP tables are going to start out empty. They're going to be populated live as necessary as traffic is flowing through this network. The routing table is not the case though. The routing table has to be populated before packets ever show up. Because if a packet shows up that the router doesn't know how to deliver, the router is just going to drop that packet. So the routing table has to be populated ahead of time, and then the ARP table is going to be populated as necessary as data starts to flow through the network. With that said, by the way, welcome to the people that just joined in chat. Welcome, Ritish. Welcome, Osama bin Lagging. That's clever. Okay. With that said, we are now going to show you everything that happens to get a packet from host A to host C. And then after that, I'll show you the response traffic. We're going to start with host A. So host A has some data it needs to send to host C. Hello, Harris. Welcome. Welcome. Host A is going to start by adding a layer 3 header to that data, which is going to include the source IP address of host A and the destination IP address of host C. Now, in lesson 3, I talked about why or how host A already knows the IP address it's trying to speak to. Possibly an administrator jumped on host A and typed ping 10.0.66.7 and provided the IP address to host A. or possibly host A acquired the IP address via DNS. One way or another, host A already knew the destination IP address it was trying to speak to, and therefore was able to put together the layer 3 header. Now host A looks at the address it's trying to speak to and compares that to the IP address and mask configured locally on host A and determines that this IP address is in a foreign network, which it is. It's going to do that through a process known as subnetting. We're not going to cover subnetting in this series. Feel free to check out the videos I've already created about subnetting. You can get them at subnetipv4.com to learn how to subnetting. Either way, host A knows that this packet now needs to be delivered to its default gateway, which is R1. The problem is that if this is the first communication that host A has ever done, at the moment, host A doesn't know router 1's MAC address. It's going to have to do ARP in order to learn the router's MAC address. So before this packet can be sent, host A is going to stop and quickly do ARP to discover the MAC address for the IP address 10.044.1. It's going to shoot out an ARP request. Excuse me. It's going to shoot out an ARP request, and that ARP request is going to ask the network if anyone has the IP address 10.044.1 to send me your MAC. And in the ARP request itself, host A is going to include its own IP address to MAC mapping. This is going to get sent out to the network. R1 is going to receive it, and upon receiving that ARP request, R1 is going to learn the ARP mapping for the sender, for host A. If I back up a second, you'll notice that this ARP request had the ARP mapping 10.044.9 to the MAC address A9A9. And that is what router 1 is going to learn in router 1's ARP table upon receiving that ARP request. Now, router 1 is going to respond. It's going to shoot out an ARP response. That ARP response is going to include the IP address of router 1 and the MAC address of router 1. That's going to arrive on host A, and once that arrives, host A will update its ARP entry to know that the 10.044.1 IP address maps to the MAC address EEE1, and that's what's going to allow host A to finish putting together that layer 2 header, which is going to take this packet to the router. Notice the source MAC address is host A's NIC, and the destination MAC address is the router's. So that's what's going to get that packet over to R1. So that will be sent to R1. Upon receiving it, R1 is going to discard that layer 2 header. The purpose of that layer 2 header was simply to go from this NIC to this NIC. It did that successfully, so we no longer need that header. Now, R1 is going to look up this destination IP address in its routing table. So 10.066.7, it's going to take a look, and it's going to see that for anything destined to 10.066.7, it should send the packet to 10.055.2. That's this guy right here. That's router 2's IP address. But the problem is at the moment, router 1 doesn't have the MAC address for router 2. So router 1 can't put together the layer 2 header it needs to get the packet across to this hop. Therefore, just like the host, the router is going to have to do ARP in order to resolve the MAC address for 10.055.2. So the router, or R1 in this case, is going to shoot out an ARP request asking for the MAC address that correlates to 10.055.2. It's going to include its own ARP mapping in the ARP request. That's going to be sent out on the wire. Once R2 receives it, R2 is going to learn the MAC address mapping for the sender, in this case R1. R2 learned that the IP address 10.055.1 maps to the MAC address EEE3. Then R2 is going to generate a response. That response includes the ARP mapping that R1 was looking for. Once that is received by R1, R1 will learn the mapping that it's trying to learn, and now R1 can add this MAC address to the layer 2 header in order to deliver the packet to R2. That is what's going to get the packet from R1 to R2. Once R2 receives the packet, R2 is going to again discard that layer 2 header. The purpose of that header was just to get from here to here. Since it did that successfully, we no longer need that header. Now R2 is going to look up the destination IP address in its routing table. It's going to find this entry that says anything destined to 10.0.66.7 should go out the left interface. And since this is a directly connected route, this tells R2 that it's actually going to be delivering the packet to its final hop, 10.0.66.7, host C. But if we look at the R2 routing table, ARP table, we can see that R2, that's a typo. That should say R2. R2 cannot construct the layer 2 header because it doesn't have an entry for the in its routing table. In its ARP table. So, just like any of the other devices in this topology, R2 is going to have to send an ARP request asking for the mapping of 10.0.66.7. It's going to send that out. Host C will get it. Host C will learn the mapping of the requester, in this case R2, and then host C will send out an ARP response. That ARP response will include the mapping that the router was looking for. Once that gets to R2, R2 will then populate its ARP table with the appropriate MAC address, and then R2 will finally be able to put together a layer 2 header which correlates to the IP address 10.0.66.7, and that's what's going to get this packet from R2 to host C. When host C gets it, host C is going to discard the layer 2 header. Again, the purpose of that header was just to go from here to here. Then host C is going to discard the layer 3 header. The purpose of that header was to go from here to here. And now host C can finally process the data. That is every single step that is necessary to get data from host A to host C. Hopefully this shows you a bit of how the routers use their routing table and use ARP as necessary in order to create the layer 2 headers to move the packet from hop to hop so it can get from end to end. Next, what I want to show you is the response traffic. And what you'll see is that the response traffic is going to go much quicker because a lot of the ARP entries have already been created. So here's what the response traffic will look like. Host C has some data to send to host A. This is probably the response to what host A just sent to host C. Excuse me. Host C knows who it's trying to speak to, so it's able to create a layer 3 header with the source IP address of host C's address and a destination IP address of host A's IP address. And since host C received something from R2 earlier, it already knows the default gateway's MAC address. Oops, that should be R2. Wow, a couple typos right there. So therefore it's able to create the layer 2 header, which will get the packet from host C to EEE4, which is R2. That's what's going to get that packet to R2. R2 is going to receive the packet. R2 is going to discard the layer 2 header. R2 is going to look at the layer 3 header in the routing table. It's going to look at the destination IP address 10.0.44.9, look for a match in the routing table. It finds it and knows it needs to sends a packet, knows that the packet's next hop is 10.0.55.1, which is this IP address right here. And then R2 is going to look at its ARP table and realize it does know the MAC address for R2, for R1. And so it can create the layer 2 header necessary that's going to take the packet from EEE2 all the way to EEE3. That is how the packet is going to be sent to R1. When R1 gets it, R1 is going to discard the layer 2 header. Again, it was only there to do this hop. R1 is then going to look up the destination IP address, 10.0.44.9. It's going to determine that that should go out the right interface. And since it's delivering something out a directly connected network, it knows that the next hop is actually the final hop before it gets to the final destination. R1 knows the MAC address, knows the MAC address for host A because it had it from earlier. Therefore, R1 can create the layer 2 header necessary to get this construct from this NIC to its final NIC, which is what will get the packet finally to host A. Host A will then discard the layer 2 header and then discard the layer 3 header and finally process the response data from host C. And that is everything that needed to happen to get the response back to host A. Hopefully you know, or hopefully this shows you that the response went much quicker because we already had the ARP entries we needed to create all the layer 2 headers necessary. And that actually wraps up our lesson on routers. Except for one final idea that I want to communicate to you. Everything that happened between R2 and R1 in order to get a packet from host C through to host A would repeat for any amount of routers in the path. Meaning, if R2 had a bunch of different routers between it and R1, everything it would do is identical. It would look up the destination IP address in the routing table to determine the next hop. It would then do ARP if needed to figure out the MAC address to create the layer 2 header. Yeah, it would do ARP as needed in order to accomplish that. So what we did a minute ago to get the packet from R2 to R1 when they were directly connected like this is the same thing any amount of routers would have done. In fact, the internet is nothing more than a bunch of routers in the path between 2 points. And so what we just discussed is really how all the routers on the internet facilitate communication for internet data. And that is actually what concludes this particular lesson. So again, I will turn it over to chat. Are there any questions over what I just went through? What did you guys think of the content that we just discussed? Go ahead and let me know in the chat. And yeah, so I'll go through some of the questions. Prestigious, welcome from South Africa. Good to see you. Rahul, hello, welcome. Harris, hello, welcome. Cool, Ratish. It will be on YouTube and it'll be the same link, so you'll be able to watch this whole replay again. Absolutely. Ali says ARP table dynamic. So typically an ARP table would be dynamic. You can manually set ARP entries if you want to, but that's pretty uncommon. Normally ARP will just essentially learn by itself and populate itself. Cool, Venkata-san, glad you enjoyed this lesson. Awesome, Lanaso, glad you enjoyed this lesson. 2 questions. Do you have good books for learning networking and DNS? So DNS has been on my list for a while to talk through. I don't have imminent plans to create DNS content right at the moment, but it is on my list at some point to get to. Insofar as what to learn, this is, if you guys are unfamiliar, this is my blog, practicalnetworking.net. What I would do is come over here, go to series, click on that. And the couple series I would suggest if you're trying to learn networking are this guy, Packet Traveling, which is kind of the article form of the video series that I'm creating now. And then also this link down in here, CCNA. If you click this guy, it's going to be a list of all the CCNA related content that I've produced. I would highly recommend reading through all of those if you're looking to pass the CCNA. I'll put both of these links in the chat as well, so you guys can take a look. Cool. You're welcome, Ali, for sure. Cool. Cool. So Venkatesh asked about dynamic routing protocols. It's really hard to kind of speak in brief about them. Really, what dynamic routing protocols are is going to be the different what each router is going to share. So for instance, in fact, let's actually go back to this slide where I talked about them. Cool. There. Cool. So each of these essentially differ in how the communication flows from router 1 to R2. It's hard to really summarize them in a little bit of time because they're all very, very deep and all go into a lot of detail. But for instance, with RIP, the entire table is shared every 30 seconds, which is useful. It's very simple. The problem, though, is that if something happens, if a particular link is to go down, within those 30 seconds, the routers aren't going to know about it and might be sending traffic to a router that doesn't know how to get to a particular destination. So RIP is sort of the simplest of these, but it does have its flaws in that it's not very reactive, it's not very fast, it's not very agile. Ospf and sort of EIGRP if you listen to Cisco's marketing, but mostly Ospf is kind of the next, the most common one you'll see in different enterprises. All the routers do what's called triggered updates with Ospf, meaning if something goes down, this router will instantly send a message to the other routers, letting them know they no longer how to get to a particular network. And then BGP is the one that's used between ISPs for the most part. That's the one that's used across the internet. The main benefit of BGP is control. It isn't about being hyper reactive. It's about having hyper control over what is shared and what is not. So those are probably the most common ones out there is RIP, OSPF, and BGP. I should really say more commonly it's OSPF and BGP. But yeah, there's your high level overview of each of them. At some point, and potentially in the full networking fundamentals course, I might actually go into the details and the differences between all of these. But for now, that's as far as actually I want to go. Cool. So John says, knowing that this list is specific to layer 3 IP regarding TCP router capability. So the routers aren't going to care about the layer 4 headers. So whether the packet is TCP or the packet is UDP, the routers don't know and don't care and don't really need to know. They just need to look at the layer 3 header and then make a decision. Now in lesson 2 of this series, of the Networking Fundamentals series, I talk about the Osi model and I talk about layer 4 and I get into a little bit of how layer 4 works, John. So if that's something you're interested in learning about, feel free to check that out. To get to the Networking Fundamentals series, just go to my, do I even have it on series? If you just go to my, I don't have it. If you just go to my homepage, it should be right there. This is the whole series, and I'll post this link in the chat as well. But right here is the all the videos that have already been created. So I highly recommend checking those out. In fact, what we just did is going to be lesson 5 of this series. Once I re-record and make it all kind of pretty and polished and edited down to, you know, fix those typos that we caught. Cool. Awesome. Glad you enjoyed it, Venkatesh. You're welcome, John. Cool. Well, that is all I had for you guys today. I hope you guys enjoyed that lesson. Hopefully that was useful. If there's any other questions, feel free to find me in Discord. I do have a Discord channel set up for practical networking that is on your screen right now, just to the, what is it, right there. You can go to that and it'll link you to the Discord. I'm hanging out on there pretty often. Feel free to pop in, say hello, ask some questions, give some feedback. That's it. That's all I had for you guys. So hopefully you guys enjoyed this live stream. Thanks for hanging out. Thanks for, the good questions in chat. If there's any other questions for me, feel free to throw them in chat. Otherwise, I'm going to call it a day. I'll be in the Discord for the next little bit if you guys have further questions. Otherwise, thank you for joining, and we will see you guys. Oh, actually, before I let y'all go. Cool. Thanks, John. Appreciate it. Before I let y'all go, this Networking Fundamentals, these videos that I'm releasing for free, they're essentially there to poll the industry to see how badly people want this content. If people really want this content, I'm actually planning to make this into a full networking fundamentals, really I should say network engineering course, because we're going to go a lot deeper into the tools the network engineers uses, TCP and UDP, different ways of doing troubleshooting, and different networking protocols, IPv6, all that fun stuff. So if that's something you'd be interested in, the best way that you can kind of bring that to fruition is by making sure as many people as possible know about these videos. Because if these videos get big, if a lot of people end up watching and enjoying these videos, that'll prompt me to actually dedicate time and energy towards creating the full course. That is the last thing that I want to teach you. Thank you for joining me. Cool. Have a great day, everybody. Enjoy the rest of y'all's week and weekend, and we will catch you guys in the next video. Please do. Much appreciated, Ali. Absolutely. You're welcome, Carl. Cool. Well, again, if you guys need anything from me, feel free to hit me up in the Discord. Otherwise, have a wonderful evening, and we'll catch you guys next time.